Introduction to FTC 1. Now, remember in what we covered just before this, we were looking at something called the area function, which we denoted as a of x. This function, a of x, essentially calculates the area bounded by a curve, the x-axis, and two vertical lines. One of those lines is fixed at a point we call a, and the other is at a point that varies, which we call x. So, as x changes, the area under the curve changes, and a of x keeps track of that changing area. The first fundamental theorem of integral calculus, we often abbreviate that as FTC1, is a really important result. It tells us something profound about the relationship between integration and differentiation. It establishes that these two operations are, in a very real sense, inverse operations of each other. Think about it like this. If you first integrate a function, meaning you find the area under its curve, and then you differentiate that result, you end up right back where you started, with the original function. So, integrating and then differentiating effectively cancels each other out. This is a key concept that will be very useful as we move forward, and we'll explore it in more detail on the following slides. Okay, so let's begin with slide 1, which introduces the first fundamental theorem of calculus. Statement of the theorem. This slide lays out the precise statement of the theorem. First, it establishes a condition. We need a function, let's call it f, that is continuous on a closed interval from a to b. Remember, continuity is important because it ensures our area function is well behaved. Next, we revisit the area function, which we called a of x in the previous slide. It's defined by a definite integral. This integral is written as the integral from a to x of f of t with respect to t, and it represents the area under the curve of f from the fixed point a up to a variable point x. Now here's the core of the theorem. It states that for any value of x within that interval from a to b, the derivative of this area function, a prime of x, is equal to the original function f evaluated at x. Mathematically, this is expressed as the derivative with respect to x of the integral from a to x of f of t with respect to t is equal to f of x. Essentially, this means if you integrate a continuous function and then differentiate it, you get back the original function. This beautifully demonstrates the inverse relationship between differentiation and integration, which is what we hinted at on the first slide. Finally, a crucial note, inside the integral, we're using the variable t. This t is what we call a dummy variable. It's just a placeholder. We could have used any letter we like without changing the result. The important part is x, which defines the upper limit of integration and therefore determines how much area we're accumulating. Keep this in mind as we move forward because it's a common point of confusion. We'll see how this plays out in the examples coming up. Okay, let's move on to slide 2, where we formally state the first fundamental theorem of calculus. Conceptual breakdown. Let's start with point number 1, accumulation. The slide states that the integral from a to x of the function f of t, and I'm using t here as a dummy variable, as we discussed, represents the accumulation of values of f from a to x. Think of it like this. We're summing up all the values of the function f over that interval. The integral isn't just giving us a number. It's building up a quantity, an area under the curve, by adding up infinitely many infinitely small rectangles. Now let's move on to point 2, rate of change. The derivative of the area function, a prime of x, represents the rate at which this accumulated area changes as we move the boundary x slightly to the right. So, imagine you're increasing the upper limit of your integral, x, by a tiny bit. How much does the total area under the curve change? That rate of change is what the derivative, a prime of x, tells us. Finally, point 3, the connection ties everything together. If we increase x by a tiny amount, mathematicians call this dx, we're essentially adding a very thin rectangle to the area. This rectangle has a width of dx and a height of f of x. The height is determined by the value of the function at that new, slightly larger value of x. Therefore, the rate at which the area is changing, that is, a prime of x, is exactly the height of the function at that point, f of x. Okay, let's break down this slide, slide 3, which really gets to the heart of why the first fundamental theorem of calculus works. Remember, we've already established that integration and differentiation are related, and we've seen how the area function, a of x, is defined by the definite integral. This slide explains how they're inverses of each other conceptually. This is the crucial insight. It shows us that differentiation undoes integration. We're finding the instantaneous rate of change of the accumulated area, and that rate is simply the value of the original function at that point. Keep this conceptual understanding in mind as we move forward, because the next slide will illustrate this with a real-world example, and then we'll work through a concrete problem to solidify your understanding. Real-world analogy, the water tank. Okay, let's move on to a real-world analogy to help solidify our understanding of the first fundamental theorem of calculus. Imagine filling a water tank. This is a scenario many of us can visualize, and it beautifully illustrates the concepts we've been discussing. Now let's define some variables. Let's say that f of t, that's ft, represents the flow rate of water entering the tank at any given time t. Think of this as liters per minute or gallons per hour. It's how quickly water is flowing into the tank. Next, let a of x, or ax, represent the total volume of water accumulated in the tank from some initial time up to a later time x. So ax is the total amount of water in the tank at time x. Now here's where the integral comes in. The total volume, ax, is actually the integral of the flow rate. We can write this as the integral from to x of f of t dt. Remember from our earlier slides, this integral represents the accumulation of the flow rate over time. We're essentially adding up all the little bits of water flowing in over the interval from to x. And finally, to find the rate at which the total volume is increasing at a specific moment in time x, we need to take the derivative of ax. That is, we need to find a prime of x, and the first fundamental theorem tells us that this rate of change, a prime of x, is exactly the flow rate at that instant, which is fx. So, a prime of x equals fx. This means that the instantaneous rate at which the water volume is changing is simply the flow rate at that particular moment. This example highlights the inverse relationship between integration and differentiation that we discussed on the first slide. Integrating the flow rate gives us the total volume, and differentiating the total volume gives us back the flow rate. In the next slide, we'll work through a specific example to demonstrate how to apply the first fundamental theorem in practice. Step-by-step example. Okay, let's move on to a concrete example to solidify our understanding of the first fundamental theorem of calculus. On this slide, we're presented with a problem. We're given an area function, a of x, defined as the integral from 1 to x of t squared dt, and our task is to find its derivative. A prime of x will tackle this problem using two different methods. First, let's apply the first fundamental theorem directly. Step 1 is to identify the integrand. The function inside the integral is t squared, so f of t equals t squared. Now, remember the core of the first fundamental theorem. It states that the derivative with respect to x of the integral from a to x of f of t dt is simply f of x. So, applying this directly to our problem, we have that the derivative of the integral from 1 to x of t squared dt is equal to x squared. And that's it for method 1. Notice how we didn't actually evaluate the integral. The theorem allowed us to find the derivative directly. Now, let's verify this result using a second method. This time, we'll first evaluate the definite integral and then differentiate. Step 1. Find the definite integral of t squared from 1 to x. The antiderivative of t squared is t cubed divided by 3. So, we have t cubed over 3, evaluated from 1 to x. Step 2 involves substituting the limits of integration. This means we calculate the antiderivative at the upper limit, x, and subtract the antiderivative at the lower limit, 1. So, we get x cubed over 3 minus 1 cubed over 3, which simplifies to x cubed over 3 minus 1/3. This gives us our a of x. Step 3. differentiate the resulting function with respect to x, we need to find the derivative of x cubed over 3 minus 1/3. Finally, step 4, apply the power rule. The derivative of x cubed over 3 is 3 times x squared over 3, which simplifies to x squared. The derivative of the constant negative 1/3 is 0. Therefore, a prime of x equals x squared. As you can see, both methods, applying the first fundamental theorem directly and evaluating the integral first, then differentiating, yield the same result. A prime of x equals x squared. This confirms the validity of the first fundamental theorem of calculus and demonstrates that differentiation and integration are indeed inverse operations. This is a crucial concept, and mastering these methods will be essential as we move forward. Common mistakes to avoid. Okay, let's move on to slide 6. This slide highlights some common pitfalls students encounter when working with the first fundamental theorem of calculus. Paying attention to these will save you a lot of frustration. Point 1. Confusing the variables. A very frequent mistake is writing the integral as integral from a to x of f of x with respect to dx. Now, let's break down why this is wrong. Remember, in the definite integral, x represents the upper limit of integration, where we stop accumulating the area. But within the integral itself, x is also the variable with respect to which we're finding the area. You can't have x playing both roles simultaneously. It creates a conflict. To avoid this, we use what's called a dummy variable. This is a variable that simply acts as a placeholder during the integration process. We typically use t or u. So, the correct way to write it is integral from a to x of f of t with respect to dt. T is just a stand-in, and x remains solely the upper limit. Point 2. Ignoring the chain rule. The first fundamental theorem, as we've seen, gives us a direct way to differentiate an integral when the upper limit is simply x. However, things get a little more complex if the upper limit isn't just x, but a function of x, let's say g of x. In that case, you must apply the chain rule. The formula looks like this. The derivative with respect to x of the integral from a to g of x of f of t with respect to dt is equal to f of g of x multiplied by g prime of x. Remember, g prime of x is just the derivative of the function g with respect to x essentially. You're differentiating the inside function, g of x, and multiplying by the derivative of the integral. Point 3. Overcalculating. Many students, especially when they first learn this theorem, feel the need to evaluate the integral before differentiating. While this approach works perfectly fine for relatively simple integrals, like polynomials, it becomes incredibly difficult or even impossible for functions that don't have an easily determined antiderivative. That's the beauty of the first fundamental theorem. It allows you to find the derivative of the accumulation function without actually having to find the antiderivative. It's a shortcut, and it's often much more efficient. We'll be practicing this in the examples, so you'll see how much easier it is. Now, on the next slide, we'll wrap everything up with a summary of the key takeaways from this section. So, make sure you've understood these common mistakes before we move on. Key takeaways. First, and perhaps most importantly, the first FTC proves a fundamental relationship. Differentiation and integration are inverse operations. Think about it like this: we've been building up to understanding that they essentially undo each other. If you integrate a function and then differentiate the result, you get back to where you started. Next, let's look at the formula itself. It states that the derivative with respect to x of the integral from a to x of the function f of t dt is equal to f of x, so we write it like this. The derivative with respect to x of the integral from a to x of f of t dt equals f of x. Remember that dt simply indicates that we are integrating with respect to the variable t. This formula is the heart of the first FTC, and you should definitely memorize it. Now, there's a crucial condition for this theorem to hold true. The function f, the one we're integrating, must be continuous on the closed interval from a to b. Continuity means that the function has no breaks, jumps, or holes within that interval. If f isn't continuous, the theorem doesn't necessarily apply. Finally, and this is where the theorem really shines, It provides an efficient way to find the derivative of what we call an accumulation function. That's the integral itself. Instead of having to go through the often difficult process of evaluating the integral and then differentiating, the first FTC allows us to jump straight to the answer. We can directly find the derivative without actually solving the integral. This can save a lot of time and effort, especially with more complex functions. Okay, let's recap everything we've learned about the first fundamental theorem of calculus. This is a really important slide, as it summarizes the key ideas. Remember, we just worked through an example on the previous slide where we found the derivative of an area function in two ways. Using the first FTC was much quicker than first evaluating the integral. So, keep these key takeaways in mind as we move forward. The first FTC is a powerful tool that connects differentiation and integration, and it's essential for solving many calculus problems.